Okay, good morning, everybody. I hope there's a few people here. Before we get started, I just want to make sure that everyone can see and hear me okay. If you can someone please type something into chat? Great. Okay. I'm glad to see that some of you are here. I'm not quite sure how many of you are here. So welcome back, everybody. I realize these are extenuating circumstances, and I just wanted to start by talking a little bit about the wider situation we're in. I hope everybody is coping and adapting okay to the COVID challenge. Just want you to know that on behalf of the faculty and the staff here at UVM, we're here for you. We will lean on each other and adapt and help each other through this process. A few housekeeping notes before we get started. We are obviously trying an experiment this morning. I have some experience using Twitch in some of my research programs, so I thought we'd try it for a lecture this morning. If it doesn't work great, I'm happy to switch to another platform. I imagine many of you have good ideas about other platforms we could use. So please do speak up if you have an idea. You can type it into chat. I'm going to stay on the stream for an hour after our lecture, which will end as usual at 9:45. So I'll have office hours here right on the Twitch stream from 9:45 until 11 a.m. I think we should use that time to talk about whether Twitch is a good platform for remote lectures. Happy to answer any questions about the course. And also, if people want to talk about COVID and lend support to each other, we can also do that during that time. How does that sound? All good? Okay, so just a few more housekeeping notes. As mentioned, there is now an attendance sheet, which hopefully you can see that will be linked to each lecture. As usual, I do want to try and incentivize you to quote unquote come to lecture and attend and participate in real time. I think it really adds to the learning experience. So please do click on that sheet. When you do, it will take you to a Google Sheet, and it should be editable by all. I see that it is. I see that most of you are here. That's great. When class finishes, I will turn that from being an editable by all to a viewable by all sheet. Now, I realize some of you have better internet connectivity than others, so as mentioned throughout this process, we will adapt as best we can. If your internet gives out on you, just send me an email whenever you're back online that you tried to attend the lecture but you couldn't, and I'll add you to the attendance sheet for today. I will take questions during the lecture as we go. Just remember that on Twitch there's anywhere between a 4 and 10 second delay, so it might take me a while to respond to your question. But please do just type it in as usual. I can't see if you raise your hand, so I'll just keep periodically checking on the chat window to see if there's any questions. Okay, as usual, let's talk a little bit about the assignments and the weekly reports. We are currently here, and undergraduates, you should be moving on to assignment 10, which is arguably the longest and the most challenging of all the assignments. What you're going to be doing in assignment 10, as I've mentioned before, is implementing phototaxis. You're going to be evaluating each robot 4 times, once with the light source placed in front, behind, and to the left and to the right of the robot. When you submit your solution to assignment 10, it is not expected that you show us in a video an evolved robot that is able to walk towards all 4 light positions. What we do want to see is that your robot isn't random. It's not walking towards one just by chance. What we're looking for is a robot that is clearly on its way to evolving the ability to approach all 4 light sources. So that's what we're looking for in assignment 10. Graduate students, you're moving on with the weekly reports. So I think that's all I have to say about the assignments. Any questions about the assignments or the final project? Okay. If not, I will move on. Okay, so we actually got partway through lecture 16 before the spring recess, which was the Golem project. So we'll start back up there and then move on to the Resilient Machines project in a few minutes. Just to refresh your memory, we're working our way through the open problems in the field of evolutionary robotics, which includes this issue of trying to cross the reality gap. How can we ensure that robots or controllers that we evolve in simulation transfer well to reality? So we started with the Golem project, which made a big splash in the media 20 years ago. And one of the things that caused such a stir in this project was not just that they were evolving robots, but according to the New York Times, that there was a robot that was making robots, and the robot making robot was this brand new thing called a 3D printer, and how that factors in we'll get to in a moment. So we started talking about this project last time. It's made up of these 3 steps. As we've seen before, we're going to evolve a robot to locomote in simulation. And in this case, this is one of the few experiments we've seen so far where they're evolving both the physical structure of the robot and its neural network controller. We saw how this was done. We have a genotype, which is made up of a list of lists. And this genotype encodes where to place various vertices, how to connect those vertices together with bars, how to grow a neural network made up of neurons and synapses, and how the genotype dictates neurons that go from synapses that go from a neuron to a particular bar, and in that bar is a spring that causes, and the motor causes the spring to extend or contract, lengthening or shortening the bar and getting the robot to move. So not that different from what we've seen before. We looked at some of the mutation operators that were applied to this robot and how it can gradually grow from a null robot into an increasingly physically complicated and neurally complicated machine. Okay, we looked at some screenshots and videos of robots last time, and I think we ended with this picture, which are this set of figures. Each figure here represents a phylogenetic tree, which represents how the population of robots are changing over time. And as I mentioned, this might be a useful figure for you in your final project. It shows in a glance some of the high-level evolutionary dynamics going on in the population. Okay, I think we got here last time. Hopefully these videos work okay. Yeah. So you'll notice a lot of these machines move using this sort of ratcheting idea. You can see the bars lengthening and shortening in simulation. You'll notice that the simulation is not perfect. Some of the objects are interpenetrating and passing through one another, which raises the question, how well will some of these machines transfer from simulation to reality? This is, remember, we're tackling the reality gap in this part of the course. Okay, so how well did they transfer? Well, in the paper itself, they described 3 different simulated robots. And you'll notice they all have different bodies, and they all move in slightly different ways. And they then used a 3D printer to print the plastic parts, which are the white parts of the robot. And they had to snap in the motors and the electronics and the batteries and so on. And given the data on the right-hand side, you can see that some robots did a better job of crossing the gap than others. The Aero robot traveled about a third as far in reality. About a third as far in reality as it did in simulation. And this Pusher robot did even worse, about a quarter as well, when transferred to reality. But for some reason, this third robot, the tetrahedron, actually transferred quite well, did much better than the other two. Why do you think the tetrahedron might have crossed the gap better than the other two robots? What is it about the structure and behavior of this particular robot that made it less sensitive to differences between simulation and reality? If you have an idea, just type it into chat. So less complex structure, maybe, depending on how you count. There are 6 or 7 parts that make up this robot. Mark Kirby says it's more stable. More stable how? So it's not necessarily more complex. Triangles are more structurally rigid, which simplifies the mechanics. Possibly. You'll notice that it does seem to have this triangular base and seems, again, intuitively speaking, somewhat more stable. You'll notice the others don't necessarily have the same strategy. Less likely to fall over. So again, that's a reminder about our discussion of legged locomotion. Anything that has to self-locomote has to reconcile various competing factors. One of them is stability. There's less surface area touching the ground, so less friction. Exactly. So if you look at the tetrahedron, you'll notice that its pushing arm is pushing somewhat more orthogonally to the ground than, for example, the Arrow robot does, and the tetrahedron manages to lift itself off the ground. So it's dealing less with the high friction of the physical carpet that you can see here. It's not clear from the simulation whether the simulated ground has high or low friction, or whether the friction matches what you see in reality, but there is something about the tetrahedron where it's able to literally and metaphorically avoid some of the differences between simulation and reality. Turns out that when you get into the details of this, it's very difficult to determine a priori which solutions are going to transfer from simulation to reality. So the idea behind the Golem project is to automate not just the design of robots, but also to automate the manufacture, so that we can pump more and more robots out into the world more quickly and more cost effectively. And those that don't transfer, and those that do transfer, do transfer. Okay. So let's talk a little bit about the 3D printing aspect of this. This was one of the very first 3D printers used back in 2000. And as you can see here, it's a deposition approach, meaning it's depositing thermoplastic. Thermoplastic is a particular type of plastic that has a relatively high melting point. So the print head is extruding liquid plastic that when it reaches the plate or the robot, the plastic cools and solidifies, and it can print arbitrary 3D structure. You can see in the bottom panel here, there is between the robot itself this interstitial material that they would place in a liquid overnight that would dissolve away some of the plastic here and leave just the robot behind. So this was, again, not just a robotics project, but a demonstration of how 3D printing could be used. The stated goal back in 2000 was to eventually print a robot that could walk out of the 3D printer. And 20 years on, we're getting closer, but we're not quite there yet. Step 3, once they had the plastic skeleton of the robot, they could snap in all the other materials. You can see here how they managed to print a 2D rotational hinge joint like you've been using in PyroSim. And you can see how exploiting the fact that a 3D printer can create arbitrary geometries allows evolution to design interesting linkages and physical structure. Okay, so one of the nice things about 3D printing, and this is more so true now than it was back then, is it's possible to actually heat up some of this thermoplastic, melt it down, and recycle it. So here it is in a in a heater, and they're recollecting the thermoplastic, which in theory could be used to create another robot. And we're not quite at the Terminator 2 stage yet, but who knows what the future holds. Okay. Okay, I'm just going to play a little bit of this video, and I'm going to just leave the audio off and speed things up a little bit if I can. So these were the investigators at Cornell describing not the robot but the 3D printer, and the 3D printer that you can see here was known as the Fab at Home project, and this was an attempt to create a 3D printer where most of the parts of the 3D printer are 3D printed. So getting back to von Neumann machines, which we talked about before the break, the idea would be, could we create a machine like a 3D printer that prints a copy of itself, that is able to manufacture another 3D printer or a robot, and that robot is able to collect materials that are used by the 3D printer to print another robot or another 3D printer, and on you go. So at that time, back in 2000, there was a parallel project going on at the University of Bath in the United Kingdom known as the Reprap Machine, and the Rep stands for replication and Rap for rapid, so rapid replication. And they really focused in this project on trying to create a 3D printer where the goal of the printer was to print as many of its own parts as possible. So I won't play the video here, you can watch it at your leisure, but imagine that you had the beginnings of such a machine. How might you wrap this technology in an evolutionary algorithm to expand or enrich this technology? What might the fitness function be for an evolutionary algorithm that is designing a 3D printer to What would be some of the desirable characteristics of a 3D printer that is doing a worse or better job of printing a 3D printer? What would be some of the reward terms or some of the penalty terms you might want to build into a fitness function where the evolutionary algorithm is evolving populations of 3D printers? The amount of material used, exactly. So a 3D printer might be able to build a copy of itself, but it might have to use 1 ton of material to build such a copy, so not very efficient. A fitness function that makes sure that each part produced is actually required, exactly. So again, we'd want something like efficiency. Other ideas? The speed of manufacture, exactly. A 3D printer could easily make a copy of itself, and it could take it a year to do so. So could we speed up the iteration time? Lifespan, so how long the 3D printer might survive before it eventually wears down. Trade-off between speed and precision, exactly. So we could evolve 3D printers that are quick at printing a new 3D printer, or efficient but not both. Evolution is good at reconciling antagonistic objectives, like we've talked about before. Evolve a 3D printer that can print another 3D printer as quickly and efficiently as possible, as accurately as possible. Structural similarity between pre-existing and newly produced parts, exactly. How good a copy of yourself can you make? What are some of the penalty terms we might want to put in? What are some of the things we might not want the 3D printer to do? Might there be some uses of such a 3D printer where the printer doesn't print a perfect one-to-one copy of itself? Overly complex parts should be penalized. Maybe the 3D printer can build a copy of itself, but made with different parts, or simpler parts, or more modular parts. Maybe we could evolve a 3D printer that builds a better copy of itself. That's a good idea. Use of too much material, again, yeah, we want it to be relatively efficient. We could imagine trying to evolve a 3D printer that prints a copy of itself but is 90% of the original size. Could we print 3D printers that print increasingly small 3D printers or increasingly large 3D printers? There are currently attempts underway to create 3D printers that print affordable homes. So maybe we would want to alter the size of the 3D printer. Kind of an interesting thing to think about, which was science fiction back in 2000, but definitely is not anymore now that 3D printers are somewhat ubiquitous. But 3D printers that print printers are still more or less on the drawing board. Might be a useful application for evolutionary algorithms. Okay, so that concludes our discussion of the Golem project, and we're going to switch now and talk about the Resilient Machines project. This was a project that I spearheaded back in 2006, 6 years after the Golem project, and I carried it out, this project, together with Hod Lipson at Cornell, who was also the scientist behind the Golem project. So you can think of the Resilient Machines project as sort of a sequel to the Golem project. Okay, so it was a sequel to the Golem project, but sort of came at it from a very different point of view. And the idea was something that we've already talked about. Clearly, robots are very useful. They're useful in indoor environments where the environment doesn't change very much. But we've had a hard time deploying useful and autonomous machines in outdoor environments where the environment is constantly changing. From the robot's point of view, it might not just be the external environment that's changing, but also the robot itself. So I'm going to show you 3 short videos that are taken from different points in the Resilient Machines experiment, and then we'll talk about these in more detail, if I can play them. There we go. Okay, so in phase 1, we're going to use an evolutionary algorithm to train a robot to walk, not that differently from what we've seen before. In phase 2, we are going to challenge the robot with an unanticipated situation that it's never experienced before, which is that we are going to pull off part of the robot's right leg. So this robot does not have a camera. It can't see itself. It has no pain receptors. It can't feel the fact that its leg has been separated. The robot simply senses indirectly through its other senses that something has changed, and this evolved neural network no longer works. The robot no longer moves forward. So the robot has to do something to recover its ability to move and continue on with its mission, which in this case is simply to move from the left side of the table to the right side of the table. And you'll notice that evolution in this case has come up with a completely different gait to allow the damaged robot to keep moving. So what we're looking at here is a resilient machine. This was one of the first autonomous machines built where once the robot is unexpectedly broken, the robot doesn't fix itself, but it adapts to the damage. So it's a machine that when broken does not stay broken. And we're going to talk about how we applied evolutionary algorithms to make this happen. Okay, so just to sort of situate this in what we've talked about so far, we've looked at a lot of experiments in this course so far, but they all sort of fall into 3 different buckets. The first one is simply evolve controllers directly on the physical robot. So if you remember back to our discussion of the first 2 evolutionary robotics experiments, the Italian group was evolving a hockey puck-sized Kepler robot to race around the top of a a desk in a maze. There was no simulation at that time. They did all the evolution directly on the robot, which has the advantage of being very simple, but it has the obvious drawback that it takes a lot of time, requires hundreds or thousands or maybe even millions of physical evaluations, and the robot will wear out long before evolution ever finds a useful controller for it. So, not surprisingly, starting around 2000, the second approach in evolutionary robotics arose, which is create a simulation of the robot, do evolution in the simulation, and then transfer to reality, which saves a lot of wear and tear on the robot, but has the major drawback of the reality gap problem. There's a third approach, which we haven't talked about too much, which is basically to create an original hand-designed neural network controller, which is difficult to do, and then allow evolution to improve on that in reality. But of course, this requires a human to handcraft the original neural network controller, which is a very difficult thing to do. Okay. So what we looked at in the Resilient Machines project, which is known in the literature as an EEA, or estimation exploration algorithm, is we actually used two evolutionary algorithms. I'm going to talk about the second one first. We're going to use a simulator to evolve a useful controller. So we're going to have a simulated robot, and we're going to evolve controllers on that simulated robot to get it to walk. But the twist here is that the simulator is not something created by hand like you've been doing over the last 10 weeks or so. Instead, the simulator itself was evolved, and it was evolved by the first evolutionary algorithm, which is evolving populations of simulators. And the fitness of any one simulator is how accurate it is, how closely it matches reality. How do we know whether a simulator is accurate? Well, we're going to collect experiences from the physical robot and feed that back into the simulator. So in the Resilient Machines project, we have two evolutionary algorithms, one which is evolving simulators, and the other one is evolving controllers in those simulators on a simulated robot. Okay, again, just a reminder, just pose any questions in chat if you have any points of clarification. I'm happy to repeat anything. Okay, so let's unpack each of these two evolutionary algorithms and see how they work. Let's start with the first evolutionary algorithm, which, as I promised, is going to be evolving simulators. How does this work? Well, instead of starting with the simulation of the quadrupedal robot you see here, we start with an empty simulator. This is sort of the gray area here. We have the physical robot. We tell the physical robot something. We tell this robot that it's made up of these 9 parts, but we don't tell the robot how these parts are fit together. So the robot has no simulator. It knows it has 9 parts, but not how they're fit together. So what does the physical robot do? It performs a random action. It pushes against the world, and it observes how the world pushes back. So in this example here, the robot has 8 motors, motor 1, 2, 3, 4 shoulders, and motors 5, 6, 7, 8. It's got 4 elbows, but it doesn't know that. It only knows it has 9 parts with 8 motors. So the robot rotates motors 1 and 5 down, and the other 6 motors up. And this is the result. And the robot has just 2 sensors. It has 2 tilt sensors on the main body that record the amount of tilt forward and back and the amount of tilt left and right. So basically this robot takes 8 numbers, sends those 8 numbers to the 8 motors, and gets back 2 numbers, the amount of tilt left and right and the amount of tilt forward and back. Okay. All right, so the robot now has that sensor motor data, 8 numbers plus the 2 resulting sensor numbers. The robot is pushed against the world and observed how the world pushes back. It is now going to start up the first evolutionary algorithm, which is going to search over a whole bunch of simulators. And you're going to see flashing at about 1 per second, you're going to see one simulator after another, if I'm able to connect to the internet here. Okay, here we go. So you're watching a snapshot of this evolutionary algorithm running, where the robot is, the physical robot is trying out one simulator after another. And you'll notice that obviously all of these simulators are not very good. They're not good descriptions of the robot's reality. If the robot were to evolve controllers using any one of these simulated robots, that controller is definitely not going to transfer from simulation to reality. However, even though we know that these simulators are inaccurate, the robot does not. And the way that this works is if you watch the green body carefully, you'll notice that in all these simulators, the main body is tilting about 20 degrees forward. And if I go back for a moment, in reality, the main body tilted 20 degrees to the right. So the fault here is actually in my camera work. When I recorded this video, I recorded from a virtual camera that was in the wrong place. So what you're actually watching in this video is the green box tilting 20 degrees to the right, exactly as the physical robot did. So the fitness of any one of these simulators is how well the virtual sensors match the physical sensors. So the virtual sensors are reporting a 20-degree right rotation, and that matches the 20-degree right rotation from reality. So far, so good? So from the robot's point of view, all of these simulators are getting maximum fitness. There's a perfect match between virtual sensor data and physical sensor data. But all of the simulators are very different. So what do you think the physical robot does at this point? What does it do with that information? It has a population of very highly fit simulators, but all the simulators are very different from one another. And get more data. Exactly. The robot sees that all of these simulators are very different from one another, and they can't all be right. The robot doesn't know much at the moment, but it knows that it can't look like this and look like this and look like this. Either all of these simulators are wrong, or one of these simulators is right and the others are wrong. So the robot needs to go get some more information. I actually, described this slide already, which is the fitness of a simulator. So let me move on. So the robot goes back to reality and performs a new action. Okay, just bear with me here. Okay, so in this case, the robot performs this action, and it's now armed with two pieces of data. It has the original 8 commands it sent to the 8 motors and the resulting 2 sensor values it got back. And now it sent another 8 values to the 8 motors and got back another pair of sensor values, right? Tilt left and right, tilt forward and back, tilt left and right, and tilt forward and back. Now the robot is going to return to the evolutionary algorithm. The evolutionary algorithm is going to continue evolving populations of simulators. What is the fitness of each simulator in that population now? What does the simulator have to do to get high fitness in this situation? Exactly. So we need to check each scenario or each action that the robot performed. So in this new population of simulators, we are now going to evaluate each simulator 2 times. The first time, we're going to send the simulator the first set of 8 motor commands and get back 2 virtual sensor values. Then we're going to evaluate the simulator a second time, send in that second pair of 8 motor values and get back 2 virtual sensor values, and then compare those 2 pairs against the 2 pairs of physical sensor data and take the overall difference between those sensor values, and that's the fitness of the new simulator. So now things are going to get more difficult in the population of simulators. They need to explain or match 2 sets of sensor data. In this case now we're going to see the simulators are all incorrect, but during this evolutionary process, you'll notice that evolution hits on an almost perfect description. Hits on an almost perfect description of the robot's body, and then that is very rapidly replaced in the evolving population by the correct solution. Okay. What you're watching in this particular, I described this as the second attempt and the second round of the evolutionary algorithm. What you're actually seeing here, this is the 8th attempt and the 8th round of evolving simulators. So we're going to go back and forth from the physical robot to the simulator, and we're going to keep going until the robot has enough information. We're going to keep doing this until the robot has enough information. And what do we mean by enough information? So this is now what the robot did on the 16th trial. So the robot now has 16 pairs of tilt data from the real world, and it's going to evaluate each simulator 16 times and measure the average ability across those 16 trials to match the physical sensor data. And in the 16th pass through the evolutionary algorithm, all of the simulators look like this. How well is the robot doing? How accurate is this simulator? Well, you can tell by looking at the image itself that obviously it's not a perfect reflection of reality. This simulated robot does not look exactly like the physical robot, but it seems to be matching these 16 experiences pretty well. So the physical robot has moved 16 times, and it has built up or evolved this simulator. We didn't have a graduate student sit down and actually create this simulation in PyroSim by hand. Evolution made it. Okay, so now let's move on to the second evolutionary algorithm, which, as I mentioned, is we're going to use the evolved simulator to evolve controllers for the simulated robot, pretty much like we've seen many times in the course so far. The fitness function here is -x, so moving to the robot's left, and you'll see that it does a pretty good job. So we now take that evolved controller and run it on the physical robot, and in this case we did a pretty good job of crossing the reality gap. So if you were sitting in the lab when this happened, what you would have seen is you would have seen the robot sitting here and moving sitting there and moving 16 times for about half a second or a second each time, and then sitting quietly for about half an hour while the evolutionary algorithm ran to improve the simulator, and then the physical robot would stand up and start moving from the left side of the table to the right side of the table. Okay, so remember we have these 2 evolutionary algorithms, one evolving populations of simulators, and the second evolutionary algorithm using the best evolved simulator to evolve forward locomotion. Okay, As promised, after that process, we moved into phase 2 of the experiment where we exposed the robot to an unexpected insult, which in this case was to send a PhD student in and mechanically separate the motor in the lower leg from the robot. So the robot can actually still send motor commands to the motor, but obviously the motor does something that has no effect on the robot's body. So what the robot senses is something has changed. So you'll notice when the robot performs, I forgot to mention, every once in a while the robot stops and replays one of those 16 actions. And here it is replaying one of those 16 actions. And in this case, instead of tilting about 40 degrees to the right, the robot only tilts about 20 degrees to the right. So the robot can't see the fact that it's missing part of its leg, but it can sense that something has changed. So the robot throws up a yellow card and says, wait, I'm going to stop performing my mission, which is to walk from the left side of the table to the right side of the table. Instead, something has changed and I need to update my simulator. So the robot goes back now to the first evolutionary algorithm and replaces that. Remember, it has 16 pairs of physical sensor data. It replaces one of those 16 pairs with the new pair that it just got back, which is the pair of sensor values that indicated something has changed. It has the original 15 plus the new 16, and at this point in time, the robot believes that it's a four-legged robot. But you'll notice that with this new information, it toys with the idea that it's missing part of one leg. It then thinks that the leg has shrunk, which doesn't make physical sense, so that idea is thrown away. And the evolutionary algorithm eventually returns to this model, the virtual 3.5-legged robot, which is the best description of what's going on so far. So you'll notice now that the simulator is changing not just in how the pieces are put together, but the relative size of the pieces as well. So we put that in as a mutation operator. We allowed this evolutionary algorithm through mutation to increase or decrease the size of objects, to simulate things like loss of a leg. Perhaps the robot is moving in a muddy environment and steps in some mud, so the leg is now bigger and heavier. The robot could simulate or approximate a lot of those experiences by fiddling with how the parts are put together, the angle at which they're attached, and how big or how small those objects are. Okay, so now the robot knows that it's a 3.5-legged robot, not a 4-legged robot. And so now it goes back to the second evolutionary algorithm, which uses the new evolved simulator to continue evolving controllers for the robot. So there's a question, how long was the training process? So this was an experiment that was run back in 2006. We did 16 exploratory trials and 16 passes through the evolutionary algorithm. Each pass through the evolutionary algorithm took about half an hour, so 16 times half an hour. It took about 8 hours to get to this point, and then a few more hours beyond this point. So about half an hour for each of these short simulated videos that I'm showing you. If you were to do this today on a GPU, it would probably take a couple of seconds. Okay, so again, we unpaused the second evolutionary algorithm, and it continues evolving controllers for this robot. The original controller that worked for the 4-legged robot no longer works on the 3.5 robot. It gets low fitness, so it's tossed out of the population by the second evolutionary algorithm, and the second evolutionary algorithm eventually converges or discovers this particular gate. And you'll notice that there's a little bit of perverse instantiation going on here. What is the perverse instantiation you can see in this video? It yaws, exactly. So we asked the robot to move along the positive X, and in this case, as it does so, it's actually rotating 180 degrees. It's moving in an arc, which is more or less fulfilling what we asked the robot to do, but maybe not in the way that we wanted it to do that. And some of you that have been working with evolving gaits for your quadrupedal robot, you've probably seen some similar things. Okay. However, when we take this second evolved controller and drop it onto the physical robot does more or less what we expected it to do. So even though the robot has become severely damaged, the robot is able to continue on with its mission, which in this case is to move from the left side of the table to the right side of the table. It doesn't move as fast as it did before. There's a little bit more perverse instantiation here than we saw before, but it is still doing a lot better than if it had just continued using the original pre-damaged controller. Okay, so what I just described to you here is this upper circle where the robot is alternating between estimating or evolving the simulator. It's trying to estimate itself and its local environment. I'm sorry, we're going between the estimation algorithm and the exploitation algorithm down here, and I apologize, this is an old image, didn't come out very well. In the exploitation algorithm, it's exploiting the best evolved simulator for locomotion. There is actually a third evolutionary algorithm that is running during this process, which I haven't talked about yet, and this is the exploration part of the algorithm. And I'll talk about that in a moment. So let's talk about this part first. So in the estimation algorithm, which is evolving populations of simulators, the phenotype, the thing that is produced by the genotype, is a simulated body and a simulated environment. And the fitness of any one simulated body or any one simulator is the similarity between the robots, the virtual robot sensor values and the physical robot sensor values. So we know what the phenotype is and the fitness function. In the exploitation algorithm, the phenotype as usual is the neural network controller, and the fitness as usual is forward displacement of the simulated robot. So let's go back and talk about the exploration algorithm for a moment. As you just saw in the video, the robot performs 16 exploratory actions to learn about the relationship between itself and its environment. During those videos, it may have looked like the fact that those actions were performed randomly, one after the other, but it turns out that only the first of those 16 exploratory actions was random, and the remaining 15 were non-random. If you were the robot, what would be your second exploratory action? As we saw in the video, let me back up a little bit. In the first exploratory action, the robot randomly decided to rotate motors 1 and 5 down and all the other 6 motors up. What would be a good thing to do if you were the robot, if you were the physical robot? What would be a good thing to do during your next exploratory action? Or if you like, we could invert the question. What is the worst thing you could do? What would be the least informative or least exploratory action you could perform at the next time? Exactly. The worst thing you could do is to do exactly the same thing twice. The reason why it's the worst thing to do is because you're not going to extract any new information from the world. Exactly. The worst would be to do the same action. So maybe you do the opposite, but the question is, what does the opposite mean here? So what we're really looking for is whenever the robot performs an action, we want it to be an exploratory action. We want it to extract the most information from the world that it possibly can. And the question is, how would the robot know how to do that with the little information it has at this point in the experiment? Remember, at this point in the experiment, it knows the 2 sensor values that were returned from those 8 motor actions, and the robot knows at this point in time that these are all good descriptions of itself. So the way that the robot does this, the way it performs the opposite, or the thing that's going to extract the most information, is it uses this third evolutionary algorithm. And this third evolutionary algorithm is not evolving a population of simulators or a population of neural network controllers. It's evolving a population of actions. So each element in the population of the exploration algorithm is a vector of 8 numbers, and those 8 numbers are the 8 commands that are going to be sent to the motors. They're 8 angles. So we have a population of actions. What would be the fitness of any one of these actions? Remember that we're going to send one of these actions in this population of actions. We're going to send it to the physical robot, and hopefully that action will cause the robot to get the most information back. A good way to start thinking about this is, again, to invert the question. Imagine that in this population, in this population of actions, we send the previous action, the one that rotates motors 1 and 5 down. If we send that action to all 4 of these cartoon simulators, these cartoon simulators are all going to do exactly the same thing. They have all evolved to explain or reproduce the action of the physical robot when they perform that one action, rotate motors 1 and 5 down. So we are looking for the opposite. We're looking for an action in this population that causes these 4 cartoon simulators to do the most different stuff. We want them to move in very different ways. So as mentioned in the chat, we're looking for difference in sensor data, and we're looking for difference in sensor data across these 4 simulators, or whatever the current population of simulators are. So the green arrows here are meant to represent one action that produces very different movements in these evolved simulators. So this is actually an old idea in AI and machine learning, that if you are acting in the world, you want to perform some action which you're most uncertain about. So the physical robot doesn't actually know, for this cartoon example, what the result is going to be. Imagine that this evolved simulator predicts that for a particular action, that it predicts that if the physical robot performs that action, the physical robot is going to tilt 20 degrees forward. This simulator says, no, 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 you're crazy, that if we perform this action, we're going to tilt 20 degrees to the right. This simulator says, no, we're not. We're going to tilt 20 degrees backwards. And this one says, no, we're not. We're going to tilt 20 degrees in the other direction. All 4 of these are in complete disagreement. So disagreement among the among the evolved simulators is a proxy or a stand-in for uncertainty. So what the robot really does in those remaining 15 actions is not to perform random actions, but very carefully designed or very carefully evolved actions that are meant to extract the most information as possible from the real world. So this is actually related back to developmental psychology, which is the study of human infants. And if you've ever watched a very small child, you'll notice that they don't sit still for very long. They're always moving all over the place. So there's an idea that's known as motor babbling or muscle babbling. So in motor babbling, the idea is, again, that it looks from the outside like the baby or maybe the robot is sort of just moving at random and trying to extract as much information as it can from the real world. But our work here actually suggested, after we published this paper, suggested that maybe babies are not moving at random, that they are trying to build up an understanding of themselves. We've talked a couple times now in this course about this idea of robots having to distinguish between self and non-self. And maybe part of that adventure is building up an understanding of self and then using multiple partial understandings of self to figure out what to do next. A common way of thinking about this is if you look outside and you look at a tree and you think to yourself about how you might climb that tree, where you might put your left hand first and then your right hand and so on. You are running a simulation of your self-model. Now, what form that self-model takes in the human brain, nobody knows at the moment, but it seems that we have one, and we use it to internally rehearse actions before trying them out in reality. However, as always, thinking about thinking is misleading. It feels like we internally rehearse actions using a self-model, but whether and how we do that is still not known. What is known is that if we force a robot to do this, it's able not just to evolve the ability to walk, but the ability to recover the ability to walk after becoming damaged. Okay. So I walked you through experiment number 1 just now, where we looked in experiment 1, the robot was able to perform 16 exploratory actions before it was damaged. And what you see in the thick lines here, the filled in lines, this is the evolved simulator. Just let me pause for a moment. The sun's coming out here in Jericho. Okay, so as we can see here, the robot came up with a pretty good description of self, but underneath, drawn in outline, is the actual body of the intact robot. And the thin black lines, which hopefully you can see here, is the amount of difference between the evolved self-model and the actual state of the physical robot. We did this 16 exploratory actions again, starting from scratch. So we wiped the robot's memory clean and it had to do it all over again. And this was the description of self that it came up with. And we did this 30 times. And in those 30 trials, we put a bold box around the experiments that were successful. And we defined successful as those trials in which the robot figured out correctly guessed which parts were attached to which other parts. But you'll notice that even in the successful trials, the angles of the parts are not quite correct. In the unsuccessful trials, you'll notice that it also mistakenly identified which parts were attached to which other parts. I see there's a question here for the exploration part here. Won't we require the actual model of the robot in order to make sense? So this is the interesting thing about this idea, is you don't actually need the correct model. All you need is for the robot to explore or search for actions that cause these partially incorrect models to differ. They have to disagree. Remember that the robot does not have ground truth, meaning the robot does not actually know how it's put together. This is not unlike a situation. Another metaphor for this idea is if you pull a jug of milk out of the fridge and the plastic is opaque, so you cannot see how much milk is in the jar. You can choose how to move that jug to figure out how much milk is in there. You're performing an exploratory action because in your head you may think that the jug is empty or the jug is full, and there are particular ways of moving that jug that will tell you whether the jug is full or empty. If you rotate the jug about its long axis, that does not help you. That is a bad action from the point of view of exploration. But shaking the jug up and down or left and right will cause your mental models to disagree. A full jug will resist acceleration and deceleration, and an empty jug will go with the flow. It'll move. So those two mental models, jug is full, jug is empty, will result in an action like this or an action like this, but not an action like this, even though you don't have an actual model of the jug. You don't actually know whether the jug is full or empty. Kind of a non-intuitive idea to wrap your mind around, but you can work it out with pen and paper and it actually makes sense. Okay, so given the self model that we got from trial number 1, as I showed you in the series of videos, we got successful sim to real transfer, and we've seen this slide before. We crossed the gap pretty well, but not perfectly. There are short periods of time during the gate in which the simulated and physical robot do not match. So this was quite a surprising result, at least to us at the time, which is that you don't need a perfect self-model. You don't need a perfect simulator to cross the gap. And you can cross the gap pretty well, and there may be little hiccups in that transferal, but it works okay. So this is pretty important, which tells us that in order to cross the sim to real gap, you do not have to have a perfect simulator. You just have to have one that is good enough. But the question is, what is good enough? And in this case, the evolutionary algorithm on its own figured out which models are good enough. So this was kind of a surprising result in the attempt to cross the sim to real gap. Okay, I think we'll end with this slide and then move on to the next lecture. What you're looking at now is some data that we pulled off of the top of the table, the physical table itself. We put a mark on the table at 0, 0 here, and we placed the physical robot exactly at that point, and we ran 30 random controllers on that robot. And as it ran those 30 controllers, we let the physical robot move for 20 seconds or so, and then when the robot stopped moving, we took a red pen and marked a red point on the table. And so looking down on the table, we got these 30 points. And the open box here is the average X and Y positions of all those 30 points. And you'll notice that, not surprisingly, when the robot runs a random controller, it doesn't go anywhere. The table's tilted a few degrees down because you'll notice there's a little bit of a bias down in the slide, which corresponds to right in the video, a little bit forward. We then took this self-model and evolved 30 controllers for locomotion. And those 30, in simulation, those 30 evolved controllers placed the simulated robot on average about 40 centimeters forward along the table. We took each of those 30 evolved controllers and ran them on the physical robot, and that caused the physical robot to end up at these 30 locations. I've circled one black dot and one blue dot. This corresponds to this controller here produced this locomotion in the simulated robot, or this displacement in the simulated robot. When we ran it on the physical robot only traveled about half as far in reality as it did in simulation, so we crossed the gap only about halfway. As you'll notice, obviously the simulator was overly optimistic. It put the virtual robot further ahead on average than it did in reality, but the blue points are much further forward than the red points are. So the simulator is still useful. It allows the physical robot, the first time it tries to walk forward along the table. Okay, while I'm changing slides here, I'm happy to take any questions if there are any. Just a reminder that we're crossing the reality gap in chronological order. We started with adding noise to a simulator from the late 90s. We looked at the Golem project in the year 2000. And we just talked about the Resilient Machines project, which I participated back in 2006. There's a question here, a statement. Most probably the differences in crossing the gap were due to friction and other uncertainties. That's exactly right. As you just saw in this experiment, the robot could alter, or the evolutionary algorithm could alter how the objects were attached together and at what angle, but it was not free to evolve the friction parameters of the simulation or other details of the virtual sensors or motors. We could, in future work, put more and more aspects of PyroSim under evolutionary control and allow experiences from physical machines to feed back and tune up those physical properties. Okay, we're going to move on now to the Transferability project. This is lecture 18, and allow me to find that for a moment. So in lecture 18, we're going to jump a few years ahead now to an improvement on our algorithm. This was a project that was reported in the literature in 2010, and this is yet another approach to crossing the reality gap. And I'm going to set up this project by asking a few questions. Obviously, what we really want to know when we're evolving controllers in simulation is how transferable they are. How well are they going to transfer from simulation to reality? So why wouldn't we just try and add the transferability of a controller to the fitness function? I see there's another question here. In your opinion, where would we use the estimation approach? As an approach, it looks tedious and very time-consuming, whereas approach 2 makes more sense if we have a physical robot. I'm not sure what you mean by approach 2. You're right, it is tedious. It takes a long time to tune up the simulator. We actually carried out that project back in 2006 for NASA. NASA is thinking about using this algorithm for situations when they send a probe to the surface of a planetary body in the solar system. Something goes wrong, but there is no time urgency. So the probe is sitting on the surface, something is not quite working. We have all the time in the world to send information back and forth from the probe back to Earth to try and infer what the problem is and infer or design a compensating controller for the robot and send it back to the probe. So when time is of the essence, this approach is probably not very useful, but the Resilient Machines project is useful when you have a lot of time on your hands. In the Transferability project, which we're going to talk about now, and maybe this is what Daniel's talking about, this transferability approach is particularly useful when you want the robot to adapt very quickly, and we'll get to that in a few minutes. Okay, so first of all, could we add transferability of a controller to the fitness function? Maybe, but how do we define transferability? The solution here might be to use two fitness objectives. One rewards for the desired behavior, which, as you'll see in this experiment, as usual, is move as quickly as possible or move as far as possible. The second fitness objective is going to reward for similarities between simulated and real behavior when we transfer to reality. So the definition of transferability is similarity between simulated and real behavior. Kind of makes intuitive sense. So if we have these two objectives, we could multiply them together, but instead in this project, they combine them in a way. They combined them in the following way. They created a two-dimensional plane that you see here, and we have one objective along the horizontal axis and the second objective along the vertical axis. Each dot here corresponds to one controller that has been transferred from simulation to reality. And we can measure for each of these controllers two numbers. The first number is how far did that controller cause the simulated robot to move, and the second number is the similarity between the simulated behavior and the real behavior. And so we can use those two numbers and treat them as coordinates for placing that controller in the two-dimensional plane. And that gives us the following picture. If we have a population of controllers, they're all sitting here in the plane. And what we would like to do is evolve controllers that move up and to the right. We'd like to get up into the upper right of this plane where we have controllers that cause the robot to move a long way. Behavior is good. And lots of similarity between simulation and reality. There's high transferability. So how do we do that? Well, to do that, we're going to use a particular kind of evolutionary algorithm called MOO, or multi-objective optimization. How does this work? Well, we start in generation 1 with our random controllers, and we measure how well they transfer to reality and how far they cause the simulated robot to move. And we then, before we move on to the second generation, we're going to tag each controller in the population with a binary tag, which we're going to call dominated or non-dominated. So what is a dominated solution? A dominated solution in the plane is any solution in which there is another solution in the population that is better at both things. So for example, if we take this particular point here, we can see that this particular point out here is both more transferability than the white controller, and it is higher in behavior. This controller causes the simulated robot to move further than this controller does. So we visit each point, and when we visit each point, we then visit every other point in the population and compare them. And if those other points we're visiting, if any one of them dominates the current point that we're sitting at, we tag it as dominated and move on to the next one. If we visit a particular point, like this one here, and visit all the other n-1 points in the population and none of them dominate this point, then we tag it as non-dominated. What you'll notice what happens, not surprisingly, is all of the non-dominated ones are the ones that are closest to the upper right. If we take a line and connect all these non-dominated points together, we get what's known as the Pareto front, named after Pareto, who actually came up with this idea in the first place. So this is the result after the first generation, which is we now have our non-dominated or Pareto front and the dominated solutions. What do you think? As we move on to the second generation, what is the first thing we're going to do? How are we going to decide which points live and die and which ones produce randomly modified copies of themselves? Remember, this is an evolutionary algorithm. Which points here are more likely to produce offspring that are up and to the right compared to other potential parents in the population? Exactly. So things are pretty simple here. We're going to delete all of the dominated solutions. We're going to delete all the dominated solutions from the population and allow the individuals on the Pareto front, the non-dominated solutions, to act as parents. So in this cartoon example here, we have 6 potential parents. We roll a 6-sided dice, and if it comes up 5, the 5th individual here, we make a randomly modified copy of it. And you'll notice in this case that the child, this particular child, is both more transferable and has better behavior than its parent. So when we recompute the Pareto front, we see that the Pareto front has moved slightly, and the previous parent is now dominated by its child and will be deleted in the population at the second generation. And if we continue this process, you can imagine what happens as we go from generation 1 to 2 to 10 to 100. We get a Pareto front that marches higher and higher up into the right-hand corner of this slide. Okay, so I think we are going to pause here. We have 1 minute left before you quote-unquote leave. Just some reminders. There will be a quiz tonight as usual. I've been recording this stream, so later this morning I will post the video of the stream to the schedule. Some of you may have lost connectivity. You'll be able to find the video there. Reading as usual. There will be a quiz posted that will be due by 11:59 tonight. As I mentioned, we will do our best to adapt to the new circumstances here. If for some reason you lose connectivity or it's hard to submit your homework, whenever you're back online, send me an email, let me know your situation, and we can try and accommodate you accordingly. Undergraduates, you're working on assignment 10. Graduate students, you're working on a weekly deliverable. I will stay on the stream here until I think about 10:30 today to answer any questions you have about the course or anything else in terms of logistics. So thanks for attending. We'll see you next Tuesday. Thanks very much.